Hello, my name is Connor O'Hara. This is Physics 2212, Lab 1, the charge tape experiment. The purpose of this experiment is to determine the excess charge on one piece of cellophane tape after ripping two pieces of tape apart from each other. To ensure relative accuracy, we're going to be comparing results between real-world data and simulated data. We must assume, to make the math easier, that the tapes will be acting as point charges. We must also be neglecting air resistance and assuming that both the two tapes we're going to be using have the same amount of charge evenly distributed among the tape. There's some underlying physical principles going on here that we need to use to accurately measure the amount of charge on the tape. One of them is Coulomb's law that states that the force is equal to K 1 over 4 pi epsilon naught times Q1, Q2, the charges between 2 points, the charges of 2 points, over the distance squared between those 2 points. There's also the electric field that is K 1 over 4 pi epsilon naught times the charge at a point over the square of the distance between that point and the observation area. Then there's the force on a charged object under Lorenz's law that states that the force is equal to QE, with Q being the charge that we're trying to find during this lab. There's also Newton's second law, F equals mg, that we're going to be using to simplify some of the math in this experiment. Now, to do this experiment, we're going to be making two 20 centimeter charged U-tapes, which U-tapes are basically just a piece of tape with the corner folded over for us to be able to grasp it easier. And we're also going to have a base tape for a common surface. Basically, you put that U-tape over the base tape, pull it hard away from the base tape, and it should come off charged. And we can check that it's charged by putting it over a table and putting something neutrally charged, like our hand. And the way charges work, and we're able to see this if we properly charge a U-tape, is that if it has any charge at all and anything neutrally charged around it, it should be attracted to it. So whether it's positively or negatively charged, it should be attracted to a neutrally charged object. But what we don't know is to whether the U-tape is positively or negatively charged. What we can do is we can take something that is that we know the charge of. In this case, we're going to be using a pen, a negatively charged pen, and we're going to make it negatively charged by rubbing it through some cotton or fabric. And I was able to experimentally tell that when I held that negatively charged pen near to a U-tape, it was repelled by it, meaning that our U-tape is also negatively charged. Our main experiment, though, is going to be using two of these U-tapes, and we're going to be eliminating the X and Z axis and only focusing on the Y-axis by putting two books to suspend our B U-tape, and then we're going to be having our A U-tape underneath the B U-tape, and they should be repelling each other, and we're going to be trying to cancel out the force of gravity on the B tape. And for me, the separation distance between the A tape and the B tape was 3 centimeters. Now we can take this and we can first we could first find the force of gravity on the B tape using the assumption that for every 1 meter, there's going to be 1 gram for the tape. And we use 20 centimeter sections as mentioned earlier. And that leaves us with negative 0.00196 newtons of downward force from the force of gravity. And so we can take that and set it equal to our previous equation to find force, which is 1 over 4 pi epsilon naught, also known as K, times Q squared. Earlier in our assumptions, we said that we were going to be setting the charges equal to each other. So we're squaring the charges over the separation distance, which we measured in the previous slide, or 2 slides ago, as 3 centimeters. And if we plug those numbers in after simplification in algebra, we're going to find that our charge is equal to negative 1.4 times 10 to the negative 8 coulombs. And if we do this, we can find the number of electrons that are in our system. And doing some math, we can find that it's 8.75 times 10 to the 10 electrons. The greater picture of this is that we need to find the ratio between the number of electrons and the number of atoms. We can do this by using n, Avogadro's constant, times the density, times the volume over the molecular weight of cellulose, which is what the tape is generally made out of.
After doing some math, we determined that the approximate number of atoms in our tape segment is 7.2 times 10 to the 19 atoms. Now, taking our two results, we find that the ratio is for one atom, we have 1 times 10 to the negative 9 electrons. Basically meaning we have a lot more electrons than atoms. So, in conclusion, we have the excess charge on the tape, which is 1.4 times 10 to the negative 8 coulombs, the number of excess electrons, 8.75 times 10 to the 10 electrons, and the ratio between the two. I did some computer modeling to quickly figure out and check my answers against a computer, and it was able to create a nice diagram of what's actually going on. This is our A tape that's being held up and having our Mg being canceled out by the forces in between the A and the B tape. Here's some hypotheticals. What if electrons have positive charge and the protons have negative charge? Basically, the interactions would be the same between the electrons and the protons, but once you start bringing in outside things, outside charged objects, mainly the pen I talked about earlier, that we know had a negative charge, when placed next to the excess electron U tape, it would actually be attracting now instead of repelling. Why is it important to handle the charged tapes as little as possible? Because when you're touching it, you're acting as basically a ground, and it's dissipating all the electrons that are sitting on top of the tape. Thank you.